Good morning, good afternoon, good evening, and welcome to my post on ghostly gravitational waves. If I predict that a ghost will appear in the castle tower every midnight, I might put a camera with a timer in the tower and attempt to capture an image of the ghost. I could repeat this process every night for a year. Perhaps the ghost only shows up at midnight on certain holidays. My hypothesis about the ghost would be falsified if none of the images show a ghost. But if I combine all of the images I've taken into one single image so that a blurry, ghostly form begins to take shape as a result of all of the dust floating around in the individual images, can I announce that I have taken a picture of a ghost? If I select only the subset of images that produce the most ghost-like form when combined, can I announce that I have taken a high-resolution picture of a ghost? I think that most people would say that the answer to those questions is no. Yet, in the scientific community today, gravitational wave and black hole physicists are doing both of these things and getting praised for their work by silly science journalists and their fans. The two culprits are the Event Horizon Telescope collaboration, which combined blurry telescope images into one image, fine-tuning calibration constants about regions of interest until what they wanted to see finally appeared. And if you click on the blog post below, you'll find links to the details of these experiments. The second guilty party is the Gravitational Wave Observatory, Ligo or Virgo. They have filtered their noisy data with a template of what they want to see. And in many ways, this is like taking a ghost-shaped filter and applying it to their data. What is fascinating about these multi-billion-dollar projects is that these sorts of basic logic errors occur at every single layer of their experimental design, and those who work on the projects show little awareness of the ways in which their work is out of line with the scientific method. In the LIGO Virgo experiment, a cursory examination reveals a complete lack of attention to earlier measurements that told them what they were trying to do was not possible, a complete lack of a control variable or consistency with their predictions. Yet they still claim success. There is a use of templates or tunable filters to extract what they want to see in noisy data. There's also the problem of their experimental design, in which it's impossible to distinguish the source of what they are measuring. It could be an air conditioner flipping on, or somebody kicking a trash can at two locations at the same time, or some combination of those two things. They also have within their experimental design an impossibility of determining the source's properties. They're trying to measure something that no one has ever measured before. But their predictions of what they think they're going to measure are themselves pure speculation. So it's epistemologically really suspect. Last but not least, the LIGO collaboration shows a lack of awareness of the limitations of their theoretical approximations. For example, LIGO claims to have confirmed general relativity by using general relativity to construct theories about black holes. Isn't this circular reasoning? Is this a dog chasing its tail? I think the answer is yes, but some people require more convincing than that. So I will go through each of the points that I listed just now. So the first is the earlier measurements that showed what they were trying to do was just not possible and that it's easy to trick yourself. In principle, the scientific method ensures that the community will correct its errors, but if it doesn't study its own history, there is no guarantee that it won't repeat its errors over and over again. Back in the 1960s, hundreds of independent research groups constructed devices to measure gravitational waves, and they all compared their results. Each research group thought that it had measured gravitational waves, but when the results were all combined, they all had to conclude that no one had been measuring gravitational waves from deep space. They had all been measuring different sources of noise. And now if you fast forward 50 years, you see that the physics community has given a Nobel Prize to a group that claimed to have measured gravitational waves with a device that is so expensive it is impossible to duplicate it enough times to make sure that it isn't just measuring noise. So I find it really strange that the physics community keeps forgetting the science lesson in which the teacher says, you must repeat your measurement under many different conditions for it to be worth anything, and you can't measure control variables. What does it mean when they're trying to measure a control variable? If you didn't pay attention in science class, I'll remind you of the purpose of a control variable. In an experiment, the control variable is not changed. The purpose of an experiment is not to study the control variable. The control is used for comparison. This is a fundamental principle of the scientific method, and LIGO, along with many other modern physics experiments, seems to be blind to it. All of the modern physics experiments which attempt to measure the noise floor of empty space, for example, LHC with the Higgs particle, COBE with the cosmic microwave background radiation, LIGO with the gravitational waves, BICEP with the primordial gravitational waves, which turned out to just be dust floating around in the sky. They're all dubious for similar reasons. They have no control variable because they are trying to measure the control variable. It's like a dog chasing its tail, or like an Ouroboros, or those snakes that eats its own tail. If your measurement tool is moving around by the same amount as the thing you want to measure, you aren't going to be able to measure it very well. If you can't have a control variable, at a minimum, your experiment should reproduce some predictions, and LIGO hasn't done this either. As of December 2019, they had announced 50 detections since 2017, but as of May 2020, they are only standing by 10 of those detections because they were forced to attribute most of those detections to known sources of noise. If I compare this to the papers they wrote predicting how many collisions they expected to see after their upgrade, these numbers are widely off the mark. They expected to see at least a few black hole collisions and at least one neutron star collision per month since August 19, and it has been 9 months. So what they did was they measured what they expected to measure, but then when they had to go back and look at their data, they were forced to reject almost all of their measurements because they could clearly see that it was a fluke. So why on earth would they still have any faith in the other measurements? It just doesn't make sense. But this is just one of many problems with this collaboration. It's like there are mistakes at every single level. even in their most basic methods, where they're taking a template and filtering their data to see what they want to see. It's like putting a filter on noise, and it's like a filter shaped like a ghost, and then saying that you've taken a picture of a ghost. The purpose of the scientific method is to make sure that you are seeing things that are really there. A scientist does not want to be biased by what he wants to see, but I'm afraid that Ligo has built bias into their experimental design by using black hole-shaped templates to filter and tune their data, sometimes by hand. In the second image below, you can see what their data looked like without their fine-tuned filtering, and it looks nothing like the black hole ring-down signature that they published in their Nobel Prize-winning paper. So then there is the issue of the scientific ethics of hand-tuned data. So in Quantum magazine, one LIGO supporter said, if LIGO did anything wrong, it was not making it crystal clear that pieces of their famous Nobel Prize-winning figure were illustrative, and the detection claim is not based on that plot. So they published an illustrated, hand-drawn figure that looked like data, and then later claimed that that wasn't the real data. I mean, this is bad. And there were these respected Niels Bohr Institute researchers who were criticizing their data analysis methods. And they went so far as to accuse LIGO scientists of misconduct and of making the conscious decision not to inform the reader that they were violating one of the central canons of good scientific practice. And this is a Nobel Prize-winning experiment. The people who founded it are still going around giving talks about this wonderful research to gullible young people. When the Niels Bohr Institute research group told LIGO that there was unaccounted for correlated noise throughout their prize-winning data, LIGO replied, and I'm paraphrasing, "We put the wrong data in our prize-winning paper, and if you look at the right data, you won't see the correlated noise. Oh, and you, Niels Bohr researchers, forgot to use an FFT windowing function, even though that is a mistake that no physicist would ever make." So the LIGO collaboration accused this respected research group that, they're experts in signal analysis. They accused them of making the most elementary mistake that no one would ever make, even an undergraduate. And based on these issues, one has to conclude that LIGO has used a ghost-shaped filter to help them see more ghosts. But this isn't even the worst of their problems. So even if a ghostly apparition or a black hole collision really happens somewhere in the universe, LIGO has no way to distinguish the signature of such a collision from some more mundane local occurrence, as in they cannot distinguish a deep space gravitational wave from a more local wave. Yet those who claim to measure black hole collisions in deep space believe that they can do this. If ghost hunters can't know if they measured a cloud of smoke or a ghost, how can LIGO know if they measured the sun burping or colliding black holes in distant space? A person from Ligo, or a ghost hunter, might respond to this criticism by pointing to the measurement they took of a gamma ray, or an ectoplasm burst, occurring at the same time that they measured a ghostly collision signature. But there again, I see evidence of mass delusion. There were 4,700 authors, or 1/3 of all astronomers in existence, on a paper about correlations between something that LIGO measured and something that gamma ray astronomers measured. But, and other types of astronomers, there are many types of astronomers, all looking at little different frequency bands of blurry light coming from a black spot in the sky. But what's weird is that the timing of the signals doesn't match up very well, and you have to wonder if a message goes out to the ghost hunting community, or to LIGO, or to the astronomers, to start looking for ectoplasm because someone thinks they saw a ghost. I think it is quite possible that ghost hunters might find a booger left by a kid and determine that it is ectoplasm. This should worry people because false alarms about weak gamma ray detections regularly prompt LIGO to dig through their noise for evidence of signals that look like black hole mergers. I won't read it because it's kind of boring, but there's a link to what the gamma ray researchers did and how often they detect spurious gamma rays, and then how often they detect these gamma rays very often, and then each time they detect them, they send that information off to LIGO and tell LIGO to go and search back through their old data. So this sort of gamma ray detection that initiates the search for correlations with LIGO happens many times per day, and when thousands of people are all expecting to see something buried in noise, I think a fluke is quite possible. I really do think that skepticism is a very good thing to hold on to when you are dealing with noisy, sensitive measurements taken by highly motivated groups of people. Maybe I am just being too strict in my interpretation of the scientific method. After all, if something dark and mysterious happens in deep space and causes the sun to burp, and that causes the Earth's core to gurgle, and that causes a lake to heat up, which causes a thunderstorm that causes a lightning strike, which hits a Schumann resonance, and LIGO detects that, did LIGO detect a gravitational wave? By the standards of the modern physics community, many people would say yes. But modern physicists do a lot of strange things in their attempts to measure unmeasurable things. Neutrinos, Higgs particles, cosmic microwave background radiation. Oh my. So the last thing on this list is the impossibility of determining the source's properties. Suppose that I believe that the blips measured by LIGO really come from deep space black hole collisions, and I believe that they have accurately estimated the size of the objects which collided, even though those estimates are absurdly larger than what they had expected to see based on other measurements and based on the theory of black holes, which they were using to make predictions of what they should see. So they're not measuring what they thought they would. Suppose I blind myself to all of that. Can I still believe in the extrapolations from these estimates that are used to determine the distance to the collision? Or have they made a mistake there as well? In the first gravitational wave announcement, they wrote that the collision was 1.3 billion light years away. I don't know what the error bars were, but science journalists never concern themselves with such trivial matters. If you detect a wave at two locations and you know its propagation speed, you can determine the direction from which the wave came, but not the distance to the thing that caused the wave. Ligo claims that they can determine the size of the objects which created the wave they detected based on the frequency of the wave. Larger frequencies correspond to larger objects. From there, you need to guess how far away such objects typically are. They use the estimates of how big they think the objects were and how far away such objects typically are to make an estimate of how big the wave should be when it gets to us. Ignoring circularity of logic, an absolute measurement of the amplitude of the wave should then tell you more about how far away it was. And since they assume that the signal traveled at the speed of light, they conclude when the event occurred. There are so many assumptions in that chain of logic, and if you are easy to bedazzle with complexity, maybe it makes sense to you. But an absolute measurement of the amplitude of their wave isn't really possible with their apparatus. Every redshift, amplification, or filtering of the signal is associated with a factor which adds an error to a determination of the absolute amplitude of the signal. And by tuning these difficult-to-determine error estimates, you can give yourself just about any result you want. So, surely the people who built Ligo were not so stupid as to ignore all of these issues. They must have had a fundamental basic research justification for this experiment. It can't have been built solely for the sake of the engineering byproducts and busywork. One would hope that the leaders of the project did not knowingly send a small army of students off on a decades-long multi-billion-dollar wild goose chase or ghost hunt. I will conclude this by unpacking the theoretical basis of the experiment in 4 layers, or different languages: a more general public language, a colloquial language, a technical language, and a sort of esoteric treatment. You can pick your favorite and fast forward to it. These languages degenerate quickly, and the esoteric and the technical arguments are the most tedious, so I will do them last. Generally speaking, by conflating relative and absolute coordinate systems and language, Ligo has convinced an influential subset of people that impossible things are possible. We can imagine having an absolute godlike perspective, but we cannot actually adopt one through our measurements, because nothing is truly stationary. That's the uncertainty principle for you. We can only measure things from a relative perspective, and Ligo's experimental design implicitly assumes it can take an absolute, godlike perspective. I find that thinking about bubbles helps illuminate the folly of this way of thinking, and in the blog post below there's a link to that description of Ligo in terms of bubbles. Colloquially speaking, if you believe in the original Michelson-Morley experiment, then Ligo cannot measure the flexing of the Earth, because if the Earth stretches in one direction, it must contract in the other. And their device is insensitive to that motion. Also, if light and matter waves change their shape in the same way at the same time, You can't use light waves to measure matter waves. In contrast, you can measure how the Earth flexes by comparing the path traveled by, for example, a particle beam in a linear accelerator to that of a light pulse with a stable arrival time. I have an article on that as well. This can show how matter ether and luminiferous ether behave in different ways. Technically speaking, previous experiments with Michelson interferometers suggested that in absolute space, light's wavelength and the interferometer cavity dimensions will change in the same way at the same time, while the amount of time required for light to be reflected by the mirrors will be constant. In relative space, the cavity dimensions are constant because they track the changes in one arm of the interferometer. Wait, gosh, I hate this scrolling. They track the changes of the general relativity coordinate system, while the amount of time the light requires to enter and exit the mirror changes, and you might wonder why they thought there would be an advantage to making the interferometer several kilometers long. In either case, the changes in one arm of the interferometer exactly counteract the changes in the other arm, such that when the Earth turns or when a wave passes through, no change will be measured at the detector. Ligo insists that they can bypass this issue by adding fresh light to the system, which allows them to sample the changes in the cavity size. This complication makes the system too difficult for most people to visualize intuitively, and this causes them to fall back on mathematics which open the door to errors of approximation. From my perspective, those who claim to understand how the fresh light concept works are akin to those who admire the emperor's new clothes. I'll try to debunk the fresh light concept in the language of reflection time. When a gravitational wave arrives, the reflection time at the first mirror and the combiner mirror are increased. If you think sequentially, fresh light that hits the first mirror gets slowed down and it will be compared to older light that has been sped up on the second mirror. The difference between the fresh light and the old light will show up as a change at the detector. This is what would happen if the laser were pulsed. But LIGO's laser is not pulsed, it's continuous. LIGO has conflated a discrete process with its continuous wave apparatus. If you think of simultaneous processes as is required for an apparatus that uses continuous waves, there is no such thing as fresh light or old light. There is just light, and you can see that the concept is nonsense, and that even starting to build anything was crazy. This collaboration uses sequential thinking for a simultaneous process, and if a person cannot mentally animate two processes occurring in parallel, then he will be more likely to believe in LIGO. In a broader sense, most of the mathematics we use in physics is an attempt to sequentially approximate simultaneous processes. And if you think about entanglement or quantum mechanics from this perspective, the concepts lose their relativistic mystery. So you wonder why they're filtering out the sorts of people who can't see these things. At this point, a determined LIGO collaborator might pull out some technical jargon. Complicated figures would be employed in an attempt to convince us that sequential, discrete analysis can be used to approximate their continuous, simultaneous process. They might say, cannot light from a laser be considered pulsed but at a fast rate, since it is produced with stimulated emission, so that light entering the vacuum arms with the mirrors are pulsed at LIGO. But by slowing the rate that light is emitted from a laser, the pulsing might become more obvious. But any non-LIGO physicist knows that stimulated emission in a laser means that the photons are emitted in proportion to the particle number squared. It is a collective, oscillatory effect in which large groups of particles oscillate in sync, making the waves they generate coherent rather than random. This process is not conducive to the emission of individual photons, as in an incoherent process. Pulses of laser light are produced through a different process, which involves giving a continuous wave a frequency chirp and sending it through a collection of dispersive elements, like prisms or diffraction gratings. If LIGO is using this justification of claiming that the fresh light is like a pulsed laser, it is yet another instance of the conflation of concepts that should not be mixed. The rate of light emission would have to be slowed to the level of individual photons for this pulsing effect to be measurable within a system designed for coherent light, and the detector would need to be sensitive to changes in the number of individual photons arriving. But direct measurement of individual photons is not possible with their system, and in any case, if the system is only sensitive to changes on the level of individual photons, it makes no sense to have the powerful continuous wave in their interferometer at all. I recall a similarly obtuse debate about the physics of the beam splitter, but I'd rather not go into that, because if I haven't lost you already, I would lose you there as well. Lastly, I will talk about the esoteric reasons that LIGO is nonsense. Esoterically speaking, in Lorentzian Maxwell's equations, the ones everybody knows, transverse and longitudinal waves will have the same speed in free space, and just as in the original Michelson-Morley experiment, if you use those equations to describe the experiment, LIGO shouldn't be able to measure anything. But if one decides that the continuous Lorentzian Maxwell's equations in relative Riemannian curved space are merely an approximation of a more discrete, grainy, recursive system described by Galilean Maxwell's equations in absolute Cartesian flat space, then there will be discontinuities between transverse and longitudinal waves, which might be measured as a sort of friction coefficient that corresponds to the strength of the ambient gravitational or magnetic field. In olden times, one would call these discontinuities magnetic monopoles, but today we call them all sorts of things: displacement currents, positrons, electrons, matter, antimatter, black holes. It all depends on your perspective. If you're really far away from it, it's a black hole. If you turn around and face the opposite direction, you first might call it a magnetic monopole, and then suddenly it's an electron. So all electrons that are behind you are magnetic monopoles, and all of the electrons in front of you are electrons. It's a question of understanding how to shift your perspective within a physics theory. And some people can't do that, yet they still become physicists. And you wonder what the physics community decides to do with them. It seems that they've decided to corral them all in strange experiments that don't actually tell us anything about physics, research, or truth, but they manage to extract byproducts from these people, for example, engineering work on a powerful laser system. maybe I'm wrong. Maybe the inventors of LIGO were trying to determine the properties of magnetic monopoles filling space. That might be worth doing. And you might at this point also remember that you learned in your first physics class that magnetic monopoles do not exist because Maxwell's equations tell us that they don't exist. That's only true if you only learn Lorentzian Maxwell's equations. If you learn Galilean Maxwell's equations, then they exist. The devil is in the details, and what's crazy is that most people don't learn the details, even if they make it through their entire career, because they don't need to know. It's sort of a need-to-know basis system. And they're lured into this field with fairy tales about how powerful physics will make them. And in the linked article below, there's a video of a woman giving a lecture on Maxwell's equations to a room full of gullible students. And she says things like, if you'd known these equations 300 years ago, you would have been very powerful. And a student just like you came from this university and won a Nobel Prize. And she says the words paradox and puzzle and mystery several times. And you just get the impression that she's selling physics to impressionable young people as a discipline that can make them powerful, noble, and famous. And she ignores the approximation inherent in setting the divergence of the magnetic field equal to 0 in Gauss's law. And I have a link to what happens if you don't do that and how Coulomb's law has to be modified. I mean, this is stuff I learned in class 20 years ago, these little caveats and details. But you have to be paying attention to get those caveats, because they're not going to help you on any of the tests. They don't test you on the subtleties and the caveats. They only test you on your ability to work with the machinery. And in fact, I think they kind of filter out the people who pick up on all of the little caveats and subtleties. And that's why I've tried to write a book on all of these little subtleties in case they're getting lost. Because there's something that's passed down in a classroom environment through a spoken tradition, and they're not in the books. They're just something that people say, and then some subset of the people in the class hears them and says, oh yeah, and then they either decide to not become physicists, or they blind themselves to all of these things and soldier on because they're focused on a more long-term goal of just learning how to work with all of these technical objects. So basically, getting back to the topic at hand, basically the concept of a magnetic monopole is just a localized swirl of space and time that exists when you don't try to measure it directly. And it's something that exists in an instant, but not over a measurable time step. So it's an abstraction. And how we define an instant varies depending on how quickly things are changing. So in a system in astronomy, an instant may be quite long. But if you zoom into a very small system, then an instant may be impossibly short. It's basically, it's relative. So these abstract objects, these magnetic monopoles, they are sort of like vortices or bubbles. They're ephemeral, ghostly little things. And modern physicists have taken to calling them particles and confusing people about the concept of antimatter, something that is relative to your perspective. A black hole is a representation of the largest particle we can think of, and when we imagine their collision in distant space, we picture matter and antimatter annihilating and releasing energy, just as we observe in our earthly particle colliders. That is why the idea of a black hole is so appealing to the physics community. Yet, just because an approximation like general relativity works on one length scale, there is no reason to believe that its approximations are valid on another. After all, space acts flat over some length scales and curved over others. And that is why approximating black holes with general relativity and thinking that they literally exist in a mathematically perfect form is just too much of a fanciful stretch for many people, or at least it's something that those who understand the difference between the map and the territory, they don't get bothered by it because they just say, it's an approximation, guys. Don't take it so seriously and don't build billion-dollar experiments to measure them. It is understandable that people are curious about dark and mysterious things. Because if black holes are like the virtual particles in colliders, then they borrow energy from the vacuum and disappear as quickly as they form. However, if the vacuum is fed by an outside source of energy, then a black hole might form and remain for a long time. If black holes exist, it tells us something about whether positive or negative entropy rule the universe, whether the energy of the universe is, if it's a closed system or an open system. It tells us something about the boundary conditions of our universe. And this has a certain quasi-religious psychological impact on many people. So in conclusion, I don't know how all physicists think, but I know two physicists very well, myself and my husband, a man who believes in LIGO measurements because he is very socially integrated into the physics community, and he conforms to their social rules of you don't criticize somebody's research that's outside of your narrow specialty because you don't know enough about it. And meanwhile, I've decided to quit working within the community and try to look at things from a more distant perspective where you see how you get out of your subspecialty and see how the system works on a larger scale. His funding sources have nothing to do with LIGO, and he is very secure in his job, but he has been conditioned to believe that it is impolite, politically unwise, and not his business to think critically about anyone's research other than his own. The politically astute thing to do in the case of LIGO is to approve of them and give them the benefit of the doubt without spending any time thinking about the issue, even though my husband, he would, on a technical basis, be an ideal person to deconstruct their engineering designs. He's like an expert in all of the things they do. But despite his long career, he genuinely hasn't given the matter 2 seconds of thought. He stopped listening to me early in my postdoctoral work when I began to think about things from different perspectives that just irritated him. And at that point, he refused to talk to me about anything related to work. Anytime I tried to explain something to him, I got shut down, and I soon figured out that the reason he shut me down was that he really couldn't understand what I was saying. His mind works in a very specialized fashion, and he just couldn't understand any of the associations I was making. So, for example, I found the following argument quite clear, but he could not even force himself to think through it because he's so specialized or even pay attention to it. So here, if general relativity is a static approximation of a more dynamic system, then its predictions about black holes will be inaccurate. black holes might not exist. Even if general relativity is an adequate approximation of a dynamic system and black holes do exist, the method of creating an image out of noisy, contaminated data is still inaccurate. Using a single result produced through faulty data analysis to claim confirmation of a hypothesis based on an extrapolation from an approximation is terrible science on multiple levels. I mean, if you tried to do an experimental design like that in medicine, they would laugh you out of the building, where they have the gold standard of a double-blind controlled experiment, where, as I've mentioned before, this experiment has no control variable, and it's not double-blind. They know exactly what they're looking for, and they have a filter that filters that image out of their data. Last but not least, a theory might be supported through results produced with many independent experimental methods addressing many hypotheses about the theory. But using multiple data analysis methods with a single data set to claim confirmation of a theory is absolutely absurd. It's crazy. And based on this list of things, you would say, those who make images of black holes and gravitational wave measurements are doing all of these things. And physicists like my husband refuse to worry about these things because they are outside of their narrow purview. It's culturally unacceptable to criticize. The best that science can do is to create a controlled experiment in which changing one variable causes another variable to change. But since this is not possible in astronomy, we must rely on astronomers to exercise extreme restraint when they interpret their data. But that restraint appears to be sorely lacking in the present-day community. I've been writing about these issues for a while, but I'm really not sure how to hit the right buttons to get the message across. I have links to 3 different articles where I've tried to attack this from several different angles, because the errors in the experimental design are at all levels, theoretical, just the design, everything. Unpacking it all is kind of tedious. It's like, it's not just saying, I found the one thing that's wrong with this experiment. No, it's happening at every level. And how they managed to create this organization that was blind to their mistakes is amazing. It's like they did testing and selected all of the people who simply couldn't see things, and then they put them in jobs where they didn't need to see those things, I guess. It's amazing how well it worked. And it tells us that this could be happening in other areas of our society, where you have systems that test and select certain types of people who have no idea what they're really doing. They're working for an organization, but they really don't know what they're doing. They could be creating a mega horrible disaster time bomb, but they don't even know it. They're just doing payroll. It's crazy. In recent months, a few physics apostates, I'm not the only one, have begun to make some noise about these matters as well, noting that Ligo has produced nothing but false alarms over the past year. As in, once they got their systems in full operation, they were forced to rule out all of the things they would have ordinarily proclaimed to be black hole mergers. And what that says about all of their earlier published detections is not good. I want to give some credit to people who I have spoken with about these issues. There's a guy on Twitter named Thaddeus Gutierrez who is taking a somewhat academic approach to being a Ligo gadfly by attempting to identify things such as lightning strikes that occurred at the same time as LIGO's claimed detections. And while he doesn't appear to be in the mainstream academic community, he is excellent at speaking their language and decoding their jargon. It's really impressive, really. And he sent me several links to papers written by more mainstream LIGO gadflies. A common thing for a young or an aspiring physicist to say is, if your ideas are so great, if you're right about everything, why haven't you published your ideas in a peer-reviewed journal? And I mean, they might not know that for an ex-physicist, ex-postdoc like me, who is unaffiliated, I mean, I left the club. Publishing in a peer-reviewed journal is insanely expensive. I can't publish. Once you lose the club, once you exit the club and are no longer owned by anybody officially, you can't publish anymore. You can't take part in the discussion. You can't score points. For example, APS, American Physical Society journals, will charge you $2,000 to publish, and Springer journals only waive their fees if you are employed by an approved institute. I found one online peer-reviewed journal called Frontiers In that didn't seem to charge at first, and it seemed to be a new model for scientific publishing in which the referees are not anonymous, which, if you've ever been a victim of a biased referee, you'd say that's very nice. But I'm a bit suspicious of it. As in all internet media, it is far too easy to distort an author's impression of their work's distribution and to distort their impression of being heard. Just this weekend, my husband has been taking part in an online workshop, and it's absurd to watch. It's just like people talking to their cameras and uploading a video of themselves talking to their cameras. It's just really weird to see. This is weird. I'm talking to my camera. But I'm not alone. Everybody's doing it right now, even people who are getting paid to do it. After putting all of this effort into debunking these giant wastes of time, I do ask myself why I'm bothering, and I think that I want to demystify the pop science nonsense that is used to lure young, gullible people into physics servitude. I think they might find better things to do with their time, and I would like to help them avoid the mistakes that I made by going into this thinking, oh, it's a paycheck, and then, 20 years later, what have I done with my life, So, for a lot of people, it's more than a paycheck. It's a community, it's a lifestyle, it's a game, and for me, I hated the whole thing. So, yeah. I don't know how I feel about it. Thank you for watching. Until next time.